Semiconductor manufacturing, from silicon to chips. Welcome to this overview of semiconductor manufacturing, your guide to understanding how everyday electronic devices are powered by complex chips built from simple elements like silicon. Semiconductor manufacturing is a fascinating journey that begins with raw materials and ends with the tiny, powerful chips that drive our smartphones, computers, and countless other technologies. This presentation is designed specifically for a general audience. Whether you're an operator, technician, engineer, or manager, the goal is to help you grasp the fundamentals of how chips are made and why it matters. We'll explore three essential areas. First, the materials. We'll dive into the role of silicon and advanced materials as the foundation for microelectronics. Next, we'll examine the processes, including lithography and fabrication steps that define modern semiconductor production. Finally, we'll cover applications, showing how these chips enable the technology all around us. What are semiconductors? Semiconductors are materials that sit between conductors and insulators in terms of how they allow electricity to flow. Conductors, like copper, allow electricity to flow easily. Insulators, such as rubber or glass, block the flow of electricity entirely. Semiconductors offer a unique middle ground. They allow the flow of electricity to be precisely controlled. This controllability is what makes them so essential in electronics. Semiconductors have several key properties. They are temperature sensitive, meaning their electrical behavior changes with heat. They are switchable, which means they can turn current on or off, just like a light switch. The most common semiconductor material is pure silicon, refined to 99.99% purity to ensure precise electrical performance. And they operate at the nanoscale, where features are built at the atomic level. These traits make semiconductors ideal for building the foundation of modern electronic devices. What are semiconductors? Everywhere around us. Semiconductors are not just important, they're everywhere. In 2021 alone, 1.15 trillion semiconductor chips were shipped globally, a testament to their integral role in modern life. These chips power nearly every electronic device we use, making them the invisible engine of our digital world. Take smartphones, for example. The A17 Pro chip found in today's high-end devices contains an astonishing 16 billion transistors. These tiny switches handle everything from your camera's image processing to mobile gaming performance. In computers, semiconductors form the core of CPUs and GPUs, delivering the processing power that drives everything from spreadsheets to AI models. In the automotive world, semiconductors are essential for smart systems, helping with safety features like collision avoidance and adaptive cruise control. And in the smart home, IoT devices rely on semiconductors for connected living, regulating lighting, temperature, and security through intelligent automation. What are semiconductors? Digital revolution. Semiconductors are the engine behind the digital revolution. Today, there are roughly 145 chips for every single person on Earth, underscoring just how essential they've become to modern life. These chips are at the heart of everything, from phones and cars to medical equipment and cloud servers. And what makes them so powerful is their speed. A single advanced chip can perform up to 17 trillion operations per second, enabling lightning-fast processing in real time. But creating these chips is no simple task. The manufacturing process is one of the most complex and demanding in the world, often taking up to 3 months from start to finish. This involves hundreds of steps, including deposition, patterning, doping, and packaging, all at the nanoscale. Semiconductors are more than just components. They are the foundation of today's connected, data-driven world. Manufacturing overview, from design concept to final product. Semiconductor manufacturing is one of the most complex and precise production processes in the world. From the initial design to the final chip, the journey typically takes over 3 months. During that time, each chip goes through more than 1,000 individual process steps, including deposition, lithography, etching, doping, and inspection. These steps are repeated in intricate sequences to build up the many layers of the chip. Modern chips are built with over 175 layers, stacked with nanometer precision to achieve maximum functionality in minimal space. And at the heart of this complexity lies the feature size, currently as small as 5 nanometers. That's smaller than the width of a single strand of DNA. Each layer must be aligned and patterned at the atomic level, making semiconductor fabrication a true engineering marvel that requires cutting-edge tools, clean rooms, and exacting control. Manufacturing overview. Semiconductor manufacturing is a complex journey that transforms an initial concept into a high-performance product. It all begins with design, where engineers create the circuit layout and define the chip's architecture. This foundational stage sets the blueprint for functionality and performance. Next comes wafer preparation. Here, pure silicon ingots are sliced into thin wafers and then polished to create a smooth, defect-free surface, ready for micro-scale processing. The third phase is fabrication, where the real magic happens. Using advanced techniques like lithography, etching, and doping, we form intricate circuit patterns and build the transistor structures layer by layer. After fabrication, every chip undergoes testing. This step ensures quality control by verifying electrical performance and detecting any defects. Finally, the chips proceed to packaging, where they are assembled into their final form, protected, and made ready for integration into electronic devices. This full journey, from design through packaging, ensures reliability, scalability, and innovation at every stage. Manufacturing complexity and industry scale. Semiconductor manufacturing demands extreme precision and control. At the core of this precision is the cleanroom environment. Facilities must meet Class 1 cleanroom standards, allowing no more than one particle larger than half a micron per cubic foot of air. Even the smallest contamination can disrupt nanoscale features. Temperature is another critical factor. Processes often require stability within plus or minus 0.1 degrees Celsius. Slight deviations can alter material properties and ruin entire batches. Lastly, patterning precision reaches the atomic scale, where devices are structured layer by layer with sub-nanometer accuracy. This complexity drives innovation and cost. Now, let's look at the industry's scale. In 2024, the global semiconductor market reached $627 billion with an annual growth rate of 19%. Fueled by AI, 5G, and electrification, demand keeps climbing. In the US alone, over 90 new semiconductor projects have been launched, reflecting major investment and a renewed focus on domestic production. Wafer preparation. The first physical step in semiconductor manufacturing is wafer preparation, which lays the foundation for all microchip structures. It begins with the formation of an ultra-pure silicon ingot. These ingots are grown using the Czochralski method, a process involving molten silicon and precise crystal pulling at extremely high temperatures, around 1,414 degrees Celsius. The resulting silicon is incredibly pure, reaching a 99.99% purity level, which is even higher than pure silver, and essential for optimal electronic performance. Once the ingot is formed, it must be sliced into thin wafers. This is often compared to slicing a salami. A diamond saw is used to cut the ingot, which typically has a 300 millimeter diameter, into individual wafers just 0.775 millimeters thick. This slicing must be uniform and precise to ensure wafer flatness and structural integrity. The high purity and dimensional accuracy of these wafers are critical, as any imperfections can lead to performance failures down the line. Wafer preparation, polishing. After slicing, the silicon wafers have a rough surface that must be refined to enable high-precision microchip fabrication. This is where polishing comes in. Using a process called chemical mechanical polish, or CMP, the wafer surface is smoothed to near perfection. CMP combines mechanical abrasion with chemical slurry to remove surface irregularities without damaging the crystal structure. Following polishing, the wafers undergo multiple cleaning cycles to eliminate microscopic residues or particles left behind. The result is a surface with atomic-level smoothness, transforming a dull, uneven wafer into a mirror-smooth substrate. This flawless finish is essential for pattern alignment, layer uniformity, and overall device performance. Final wafer specifications are tightly controlled. The diameter is 300 millimeters, and the thickness is precisely 775 microns. Surface quality is classified as mirror-like, and defect density is maintained below 0.1 defects per square centimeter, meeting the industry's highest standards for precision and yield. Wafer preparation, precision requirements. In semiconductor manufacturing, precision isn't just important, it's critical. During wafer preparation, tolerances must be kept within incredibly tight specifications. One key metric is thickness tolerance, which is controlled within plus or minus 1 micrometer. That's about 1/100th the thickness of a human hair. But it goes even further. The surface roughness of a wafer must be less than 0.1 nanometers. That's subatomic scale precision. This ultra-flat surface is essential for subsequent layers of circuitry to align perfectly. Here's a fun fact that puts this into perspective. A single 300 millimeter wafer can produce thousands of chips, and the surface is so remarkably smooth that if scaled up to the size of planet Earth, the tallest bumps would only be about 6 feet tall. That level of uniformity enables the kind of advanced computing power we rely on every day, from smartphones to satellites. Lithography process. Lithography is a critical process in semiconductor manufacturing that enables the creation of microscopic patterns on a wafer using light. At the heart of this process is the use of a material called photoresist, a light-sensitive coating applied to the wafer's surface. There are two main types of photoresists: positive and negative. Positive resist becomes soluble when exposed to ultraviolet light, which allows the exposed areas to be removed, leaving the protected areas behind. Negative resist behaves oppositely. UV light hardens it, so the exposed areas remain, and unexposed areas are removed. Positive resist is preferred in the industry, used in 95% of applications, because it enables higher resolution patterning, essential for advanced lithography. Major suppliers of photoresist include Fujifilm Electronics, Dow Chemical, and JSR Corporation. These companies play a key role in supporting precision manufacturing across the semiconductor industry. Pattern transfer, from reticle to wafer. The lithography process involves transferring a microscopic circuit pattern from a reticle or blueprint onto a silicon wafer using ultraviolet light. The first step is to coat the wafer with a light-sensitive material called photoresist. This coating is essential because it reacts to light, allowing for selective patterning. Next, ultraviolet light is projected through the reticle, which contains the desired circuit pattern. This light passes through a series of lenses and mirrors that shrink and focus the image to a much smaller scale, achieving the high precision required in semiconductor manufacturing. Once the pattern reaches the photoresist-coated wafer, it is exposed. Finally, the wafer undergoes a development process, where the exposed or unexposed areas of photoresist are removed, depending on whether a positive or negative resist is used. The result is a 3D relief pattern that defines the layout for subsequent processing steps. Light types and precision in lithography. Lithography uses different wavelengths of light to achieve various levels of precision in chip design. DUV, or deep ultraviolet light at 365 nanometers, is used for simpler, less complex chip patterns. For higher resolution features, advanced DUV at 193 nanometers is employed. The most refined detail is achieved using EUV light, extreme ultraviolet, at just 13.5 nanometers, enabling the finest chip structures. With these technologies, lithography reaches atomic-level accuracy. Feature sizes can go down to 5 nanometers, with overlay accuracy of plus or minus 1 nanometer, and pattern fidelity at 99.9%, ensuring the circuit matches the original design almost perfectly. Smart correction powered by AI plays a key role, optimizing each pattern with a 99% success rate using computational lithography. An amazing fact, EUV features are so tiny, it's like writing with hair-width precision on a football field-sized surface, an astonishing scale of control. Step 3. Etching. Carving 3D patterns with precision. Etching is a vital step in semiconductor fabrication that sculpts three-dimensional patterns into wafer layers. There are two primary etching methods, dry and wet. Dry etching uses reactive gases in a plasma state to achieve high precision, excellent control, and superior anisotropy, meaning the etching is highly directional. It is the primary method used in advanced manufacturing today. In contrast, wet etching relies on chemical baths. It is faster and more cost-effective, with good selectivity, but offers less control and precision than dry etching. Critical control during etching is essential to avoid damaging underlying layers, especially with devices stacking up to 175 layers. Etch depth accuracy must be within +1 nanometer. Key suppliers include Lam Research, the market leader, Oxford Instruments, offering advanced systems, and Semis, a regional player. Each contributes to meeting the demanding standards of today's complex semiconductor architectures. Etching process, removing resist and creating patterns. The etching process is used to remove specific parts of the photoresist and underlying material to create the final 3D pattern on a wafer. Before etching, exposed areas of resist are clearly defined, usually after the development step. The first step is to bake the wafer, which hardens the photoresist and improves its resistance to etchants. Next, an etchant, either a reactive gas for dry etching or a chemical liquid for wet etching, is applied. This etchant removes material from the exposed areas of the wafer. Once etching is complete, the degraded resist is stripped away, exposing the newly formed 3D pattern. The final step is cleaning and inspecting the wafer to ensure the pattern is accurate and free of defects. This sequence, bake, etch, strip, and clean, is essential for ensuring precise, repeatable pattern transfer in semiconductor manufacturing. Step 3. Etching. Etching is a vital process in semiconductor manufacturing, especially for 3D NAND devices where structures are vertically stacked. Today's 3D NAND devices can have up to 175 layers. This creates a significant challenge in precisely carving through the entire stack while maintaining pattern integrity. The high aspect ratio of 60.1 makes etch depth control especially critical. Small deviations can lead to serious defects, which is why depth control is marked as a critical parameter. The process must also manage high selectivity, 50.1, so that the desired material is etched while the underlying layers are preserved. Precision is closely monitored. Etch rate control must stay within plus or minus 0.5% to ensure uniform trench profiles. Uniformity must be better than 2% across the wafer. CD, or critical dimension, control is maintained at plus or minus 3 nanometers to preserve circuit integrity. Altogether, etching demands extreme precision in every parameter. Advanced etching. To define the finest features in modern semiconductor devices, advanced etching techniques are essential. Multiple patterning strategies such as double and quad patterning are used to multiply the resolution of lithographic tools. Double patterning divides the original pattern into 2 masks to etch finer details. Quad patterning pushes this further by splitting the design into 4 separate exposure steps, enabling even smaller features. Spacer-based techniques, especially self-aligned methods, further enhance precision. These use deposited spacer layers to define features with sub-lithographic dimensions, offering tight control over pitch and placement. One of the greatest challenges in advanced etching is creating deep, narrow trenches, down to just 5 nanometers in width and 300 nanometers in depth. This must be done without damaging the trench sidewalls or triggering structural collapse. Such precision requires optimized plasma conditions and excellent control over profile shaping and etch chemistry. Step 4. Ion implantation. Ion implantation is used to precisely control the electrical properties of silicon by introducing dopant atoms. Pure silicon has medium electrical conductivity, making it neither a full conductor nor a perfect insulator. After ion implantation, this conductivity is finely tuned based on the type and amount of dopant introduced. There are two primary doping types, N-type and P-type. N-type doping uses elements like phosphorus or arsenic, which contribute excess electrons, enhancing conductivity and creating negatively charged regions. P-type doping, on the other hand, uses elements like boron or aluminum, which accept electrons and introduce holes, resulting in positively charged regions with modified conductivity. This doping process enables the formation of transistors, tiny switches that control current flow. Today's advanced chips can contain up to 16 billion transistors, each switching states to perform calculations. Ion implantation is foundational in building these high-performance microchips. Implantation process. Ion implantation modifies the electrical properties of silicon by bombarding it with high-speed ions. These ions are sourced from a controlled ion beam, and their energy levels can be adjusted, ranging from low to medium to high, based on how deep the ions need to penetrate the silicon wafer. The end result is a doped wafer with finely tuned electrical behavior. To achieve the desired outcome, several key parameters must be precisely managed. Dose refers to the concentration of ions implanted into the wafer, which directly influences conductivity. Energy determines how deep the ions penetrate the material, shaping the vertical profile. Angle controls the direction at which ions hit the surface, which is critical to avoid unwanted channeling effects. Finally, temperature during implantation plays a key role in maintaining crystal quality and minimizing damage. Together, these parameters ensure accuracy and consistency in device performance. Ion implantation specifications and benefits. Ion implantation systems offer a wide range of precise control parameters. The energy range spans from 1 to 200 keV, allowing control over how deeply ions penetrate into the silicon. The dose range, which defines ion concentration, can vary from 10 to the power of 12 to 10 to the power of 16 ions per square centimeter. Depth control is finely tuned to within plus or minus 5 nanometers, ensuring consistent electrical properties across devices. Uniformity is also excellent, kept below 1% variation across the wafer. Several leading companies dominate the equipment market. Applied Materials is the market leader. Axcelis Technologies specializes in ion implantation. Ion Beam Services provides advanced technologies, and Sumitomo Heavy caters largely to the Asian market. Key benefits of ion implantation include precise dopant placement, operation at room temperature, and the ability to repair damage through post-implantation annealing. This next step involves heating the wafer to 900 degrees Celsius for 30 minutes to activate dopants and restore crystal quality.